Viewers, welcome to our channel. This is a question from December 2019 CSIR NET Mathematical Sciences. This is a question on abstract algebra from part C, and here we are asked that if C is the set ring of all real valued continuous functions on closed interval 0, 1 and A is as shown, then which of the following are true? First of all, C is a ring of real valued continuous function. This is a commutative ring with unity. A is the set of all continuous functions on closed interval 0, 1 such that f vanishes at the point 1/4 and 3/4 simultaneously. Now, the 0 function clearly belongs to A and hence A is non-empty. Now, if f belongs to A and g is any function from C01, then f belongs to A, so f of 1/4 is equals to f of 3/4 is equals to 0, and fg of x is defined as fx into gx for all x in closed interval 0, 1. Now, fg at the point 1/4 is f of 1/4, g of 1/4 is equals to 0 into g of 1/4. Whatever be the value of g 1/4, this gives us 0. Similarly, fg of 3/4 is also 0. Thus, fg belongs to A. Since C01 is a commutative ring, so gf also belongs to A. Thus, A is an ideal of C01. Now we check the first condition. A is an ideal in C01, but it is not a prime ideal in C01. A is an ideal of C01. We will check whether A is prime or not. Now, we consider two functions. Fx is equals to 0 when 0 less equals to x less equals to 1/4, x minus 1/4 when x is greater equals to 1/4. It looks like this: 1/4, 2/4, 3/4, 1, and it looks like this. Clearly, f does not belong to A, since f of 3/4 is equals to 3/4 minus 1/4 is equals to 2/4 is equals to half, which is not equals to 0. Also, consider another function gx is equals to the function defined as this is 0, this is 1/4, this is 2/4, this is 3/4, this is 1. If we define a function like this, if g of x is if we define gx as modulus x minus 3 by 4 for all x belongs to 0, 1, then it will look like this. This is gx. Clearly gx also does not belong to A, since g of 1/4 is 1/4 minus 3/4 modulus gives us minus 2 by 4 and hence half, which is again not equals to 0. But the function fg is clearly belonging to A, since fg of 1/4 is equals to f of 1 by 4, g of 1 by 4. F of 1 by 4 is 0, which is 0. Again, fg of 3 by 4, f of 3 by 4, g of 3 by 4. F of 3 by 4 is half, g of 3 by 4 is 0, and so this is 0. Fg belongs to A, but neither f nor g belongs to A. So A is not a prime ideal of C01. A is an ideal but not a prime ideal. Thus, our option 1 is correct. Now, we have checked that A is an ideal but not a prime ideal. 1 is true. We have checked that A is not a prime ideal, so 2 is false. For 3 and 4, C01 is a commutative ring with unity, and we have checked that A is not a prime ideal of C01. Now, if A is a maximal ideal, we will check what happens. If A is a maximal ideal, then C01 factor A is a field. This comes from two theorems. First of all, let me write two theorems, that if R is a commutative ring with unity, then I is number A, a prime ideal if and only if the factor ring R factor I is an integral domain, and I is a maximal ideal if and only if the factor ring R factor I is a field. So, if I is a maximal ideal, if and only if R factor I is a field. If R factor I is a field, then this implies that R factor I is an integral domain and by point A, this implies that I is a prime ideal. So for any commutative ring R with unity, if I is a maximal ideal, then I is also a prime ideal. Now C01 is a commutative ring with unity. If we suppose that I is a maximal ideal, then we will, by our discussion, we can easily conclude that I is also a prime ideal. But we have checked that I is not a prime ideal. So A is not a prime ideal. So A cannot be a maximal ideal. Thus, our condition 3 and 4 are ruled out. Condition 3 says that A is a maximal ideal in C01. So we check that A can't be a maximal ideal in C01. And 4 says that A is a prime ideal but not a maximal ideal. So this is automatically false since A is not a prime ideal as we have checked. Thus our only correct option is 1 is our only correct option.